And our first speaker is Alessandro Sfondrini, who will tell us about how to tune Ramond-Ramond flux for ADS3 strings.
Thank you very much, and it's a pleasure to be here. I'm very grateful to the organizer for this opportunity to present some of my work and also to review some more general work about advances in understanding ADS3 CFT2, the so-called tensionless limit, how to put Ramond-Ramond flux in it, and all that. So just to remind you, when you are dealing with ADS3 backgrounds, there are some maximally symmetric backgrounds. They're all of the form ADS3 cross S3 cross something else. Could be T4, could be a K3, or another S3 cross S1. And they should all be dual to theories with n equal 4,4 supersymmetry in 2 dimensions, though these dual theories are largely unknown. Here I want to talk about the simplest of these theories, which is ADS3 cross S3 cross T4, which is already complicated enough. And I want to look at the simplest non-protected observable, perhaps, which is the planar spectrum. So the spectrum in the large n limit of whatever dual theory or J string to 0. ADS3 cross S3 cross T4, even with 16 supersymmetry, is a family of backgrounds. There are a bunch of very interesting parameters that I'm going to discuss. First, let me remind you that ADS3 has a symmetry that is factorized, is 2 copies of SL2R. And I will denote the generators as L for one copy and L tilde for the other copy. There is a similar split for the symmetry of S3, is SO4, so you get 2 SU2s, and there is a J and there is a J tilde. So I will use this notation throughout the talk. I will also dot the indices of the tilde generators. When I talk about the spectrum, I talk about the energy spectrum of strings. It's related to global time in ADS, and is related to these generators, L0 plus L0 tilde. It's the only non-compact generator that you have in the game, so it's the interesting one when you want to look at things that are not protected. There is also another combination that is interesting and useful, is called the light cone energy, which I call H tot. It's just E minus J. It will play a role later, so let me just introduce it now. J tot is the total R charge, J plus J tilde. The simplest family of backgrounds comes from a system of NS5 branes and fundamental strings, and I take the number of fundamental strings to be large. That will be my large n limit. And what you get here is a background with a metric, a B field, which is basically such that H is just the volume of ADS plus the volume of the sphere, and no Ramond-Ramond flux, and the dilaton you can put to 0. So the only parameters here is a discrete parameter that comes from the number of branes K, 1, 2, 3, 4, etc. And in fact, if you pick dimensionless units, so you make the radius of ADS and of the sphere to be 1, then the tension, the dimensional tension of the string, is basically K, is K over 2 pi. So that's the discrete parameter in this game. And the reason why this background, I call it simplest, is that it so happens that the string action, when you write it down, is the action of a Vesuminov-Witte model. And this is something that you know how to quantize, even in the supersymmetrized case. And you can quantize it in the RNS string. This is all very old story, but I want to briefly review it. So you get a Vesuminov-Witte model based on SL2 and SU2. The levels of these Kac-Moody algebras are shifted by plus and minus 2. That's why these things that I'm saying hold for K greater than 1. K equal 1 is a bit special. Let's set it aside for now. And then you get a bunch of free fermions, and you get some free bosons from the T4 direction. And very roughly speaking, what you do is that you generate the spectrum by freely acting with the modes of the Kac-Moody currents and the modes of the free bosons and the modes of the free fermions in the RNS string. You take some reference state, you act with these modes, you get a candidate state psi. Then you have to impose some physical state condition, which is the Virasoro constraint, and that gives you some quadratic constraint. At the end of the day, you can write down the energy in closed form. I'm not deriving anything, I'm just telling you the story. And the energy looks something like this. It's given by some square root because it comes from solving some quadratic constraint. Because our constraint is quadratic because of the Sugawara construction, for people that are familiar with these words. So, just to say, what do we have? We have a state which is more or less freely generated, and an energy level, which you can write in closed form, is very, very simple, and it's also very, very degenerate. If you have a very large number of oscillators, or total number of oscillators that is very large, you see that you can create many, many states that are made out of different stuff, but have roughly the same energy, or exactly the same energy. So this is not something that is typical. If you think of ADS5, if you think of the spectrum of something like the Konishi operator, it looks nothing like this. It's very complicated. You have to expand the coupling in maybe 1/k. The coefficients are zeta function, multiple zeta function, things like that, right? So it's very different, and also all this degeneracy is very spatial of this set of Bazumino-Witten backgrounds. In fact, it's much more similar to flat-phase strings. So there is also, by the way, a long string spectrum. I don't want to talk about it. It's not super relevant to my talk, but there is a whole story there. So the idea is, how typical is this? Not very much, because we can turn on more parameters, and one important parameter is the Ramond-Ramond flux. You can start from the system of branes. You can turn on an axion in the system of branes, and that gives you a continuous parameter. And what you get is now a background that has Ramond-Ramond and an SNS flux, and you see the coefficients are q and square root of 1 minus q squared, so their square sum to 1. And you interpolate between something with just an SNS and also this Ramond-Ramond flux. If you start at a fixed k and you turn on the Ramond-Ramond flux, the tension grows. So the tension blows up if you send q to 0, so if you go all the way to the Ramond-Ramond. A better way to visualize what you're doing is to keep as parameters k, which is discrete, and instead of looking at the tension or q, just look at the coefficient of the Ramond-Ramond tree form. And you get two parameters. One I call h, which is continuous, and k, which is still discrete. They are basically what appears in front of the tree forms, scaled by the tension. And you see that the tension is sourced in more or less equal measure by the Ramond-Ramond and the NS-NS flux. So every time you add a bit of either, you generate more tension for the string. And when you do this, the expectation, which to some extent you can compute in some regimes, is that all the degeneracy that I introduced lift, and the spectrum becomes much more complicated. However, it's very difficult to compute this in the RNS formalism, especially if you want to do it when the amount of Ramond-Ramond flux is much larger than the NS-NS. You can do it perturbatively, but not in general. By the way, there is also a family of background that are only Ramond-Ramond. They don't have any B field. The K is 0. They are just sourced by the Ramond-Ramond tree form. Those are even harder to describe in the context of the RNS string, but they're very interesting because they're related to the near horizon limit of the D1, D5 system. So integrability for this background provides an alternative way to study all of the spectra of all of these backgrounds. At the classical level, this model, the string nonlinear sigma model, is integrable for any values k and h. And that allows you to basically come up with a scheme to quantize the Green-Schwarz action in light cone gauge. And this leads you to a set of equations for the spectrum for any k and h. And that's what I'm going to review. Briefly, what is this light cone gauge? Well, you just take a coordinate on the sphere, an angle. You take time in ADS. You package them in some light cone coordinates. You say that x plus is equal to tau, and then the density of p minus, the conjugate momentum, is equal to 1. This is sometimes called the uniform light cone gauge. The upshots is that the Hamiltonian on the worldsheet, so the thing conjugates to time on the worldsheet tau, is now this H total, the total light cone Hamiltonian that I introduced before, which is L minus J in the left plus L minus J in the right. The other thing that is notable is that the size of the worldsheet is fixed, which is normal, and it is fixed in terms of a charge, in terms of the total J. Now you can look at the symmetries of this light gauge fixed theory. First of all, let me remind you the total symmetry algebra is called PSU1,1/2. It fits the SU1,1 and the SU2 that we had before, and it comes into copies. And this combination L minus J is actually quite nice because it's precisely the BPS bound of either copy of the algebra. So H and H tilde, that together make H dot, are both positive semi-definite, and they are 0 only if the state is BPS. So also the total Hamiltonian becomes positive semi-definite. So that's a nice advantage. And then the generators, the fermionic generator of this PSU1,1/2, there are 8 supercharges for the left algebra and 8 for the right. They have indices alpha, which are our symmetry, M, which is the SL2 index, and then they have another index A, which is just the statement that they are in 2 copies. So there are 8 plus 8, 16, as promised, half of ADS5. But not all of them exist in the light cone gauge. In the light cone gauge, you are going to break some symmetries. In fact, since our light cone gauge choice is half BPS, we are going to lose half of the supersymmetries. They are going to be non-linearly realized. So which ones are the ones that survive? Well, it turns out that they are the ones where if you pick the R charge to be positive, then you pick the SL2 charge to be negative, and so on and so forth. So you have to pick these signs in some consistent way so that they are annihilated by L minus J. And similarly for the right, so you go down to half of the supercharges. Then you can study in light cone gauge, for instance, semi-classically, what algebra these make. And what you find is that there is a trivial part, which is just a subalgebra of PSE 1,1/2. So a G with this other G, which is basically its conjugate, it gives you H. It gives you the left part of the total Hamiltonian, L minus J, similar for the tilde. And then there is a part which is maybe less expected, is a central extension which is not part of PSE 1,1/2 because it couples the left and the right copies. So you find that a G with a G tilde, they don't anticommute to 0, but they anticommute to some charge. And this charge is a bit funny, you see, because it carries some indices of R charge. It carries a plus of the left and the plus of the right R charge. So it's a charge that increases, is central, so to say, because it changes the total ground state R charge of your chosen vacuum of the light cone gauge. This is all fine as long as you take your vacuum to have very large R charge. So you take the cylinder, and instead of having a cylinder, you make it into a plane, and then you can make sense very easily of this action. There is no problem. You decouple, essentially, the generator corresponding to the total R charge. This type of central extension is actually very, very similar to what we have in ADS5, famously found by Beisert in unequal force Supriya Mills, then found again in the ADS5 context. And I'm going just to call C and C dagger the C++ and C minus minus because they have too many indices. They are a bit funny because they're not part of the original algebra, but if you go and compute them, for instance, semi-classically, you find that they look quite nice and quite reasonable. So now you have your large worldsheet. It's basically a plane. You put some excitation that corresponds to the modes of your transverse bosons, fermions of the light cone gauge. And you create a scattering state, essentially, an asymptotic state with a bunch of particles in it. And you compute what is the eigenvalue of this central charge, and you find that it has this curious form. First of all, is immediately directly related to the amount of Ramond-Ramond flux. It's not there if you don't have Ramond-Ramond flux. Second of all, it happens to be 0 if this state happens to satisfy the level matching condition. So the central extension is not there for physical states, but it is there if I just want to look at the algebra or the symmetries acting on a single oscillator here, which is actually quite useful. So I want to keep track of this structure. It's actually a very constraining structure. In fact, immediately one thing that it tells me is that these oscillators have to transform in particular representation of the algebra which I showed you that satisfy a quadratic constraint, which is basically a shortening condition of the representation. And from this condition that involves H and H tilde, which are related to H dot, I can extract an exact dispersion relation for each of these oscillators. If I create a particle of momentum P on this worldsheet, I can find its energy, and if I have many particles, it will be just the sum of the energies. The form is very curious, very interesting. So it's this expression here. P is the momentum of my excitation on the worldsheet. K and H are the parameters of the background, the NS and Ramond-Ramond flux. And this mu is just a label that distinguishes the fact that you can have different representation. It's not important what they are right now, but there are essentially K minus 1 different representations that you can construct. Just to give you a little bit of a flavor, if we go back to the simple Vesuminov-Witten case, so H is 0, this square root here becomes just an absolute value, the square root of a square. And that means that you can have excitations that move at the speed of light to the right or to the left, and they will be charged only under either H or H tilde. The dispersion relation came from a relation which was H times H tilde equals C times C dagger. If you don't have C, it's H times H tilde equals 0, so you can have H or H tilde, but you can't have both. If instead you go to the opposite setup, the D1, D5 system, so you kill this K and you keep the H, you get this lattice-like dispersion relation, and this mu can take any values. All right, that's the dispersion relation, just if you are treating these as free particles, but these particles are not free. There is some interaction Hamiltonian. These interactions we capture through an S matrix, and this S matrix, I'm cutting a long story very short, is fixed essentially by symmetries. So if I have a couple of particles, I can scatter them, and there is a tensor part which I can fix uniquely, and the prefactor, which is a bit harder to fix, I need unitarity, crossing, analyticity, all sorts of considerations. The other part is just solve linear equations to get. And then there is an integrability recipe that tells you how to find the correct spectrum when you have these ingredients. And it is, well, you were in infinite volume. J was infinite. Put it back to a finite value and put periodic and boundary conditions. So some sort of e to the IP L, total volume, equals to 1. But you have to correct this e to the IP L equal to 1 by the S matrix. These are sometimes called the Bethe-Ansatz equations or asymptotic Bethe-Ansatz. They give you a quantization condition for the momenta of the type that P is 2 pi some integer over L plus corrections. These corrections will have to do with the interaction with the different P's and so on and so forth. And then you just plug these P's and you put it in this H and you find your energy up to other more complicated corrections that I don't have time to discuss, but that in principle are under control as well. Just harder to find, and they go under the name of thermodynamic Bethe-Ansatz or quantum spectral curve, if you have heard the names. So with this machinery, what do we find? We find that for H equal to 0 and any K, we are in the Vesuminov-Witten setup, we can reproduce the spectrum that you get from the Vesuminov-Witten model. That's great. It's necessary, so it's good that we find it. In the D1 device system, opposite limit, K is 0, but you have any other H, we can find the spectrum. We have equations for the spectrum, and they have interesting features that I will show you in a moment. And they don't look like anything else that people have studied in this context, as far as I know. And then there is the most general case, where you have both parameters and you can start playing with them. And very recently, we arrived at the step of fixing completely this S matrix and these dressing factors. So we still have to do the part where we find the equations, but this is something that I would hope would happen in maybe a few months, maybe a couple of years. Okay, this was an overview. Now a little bit of physics, finally. And the interesting physics, for instance, is what happens when you go to small tension, when you're trying to understand something about the duals. Remember, the tension was sourced by K and H in this way. So if you want to go to small tensions, there are, well, two ways. The most natural would actually to say, well, K should be 0, and H should be as small as possible. And that's something related to the D1 device system. But there is another tensionless limit, as it is called, which actually has a little bit more tension. It's K equal 1 and H very small. And that's related to this famous symmetry product orbifold CFT. So let me tell you about the latter first, and then I'll go back to the D1 device system. So symmetry product orbifold CFT, crash course. What does it mean? So that's meant to be the dual. It's actually demonstrated, I would say, to be the dual of K equal 1, H equals 0 strings in this case. You take a theory with 4 bosons, supersymmetrized fermions, and n equal 4 supersymmetry. You take n times the tensor product, and you mod out by the action of the symmetry group. These theories have been studied a lot. They are fairly intricate, but some parts of them can be studied. They're not too hard. So the idea is that a general state is labeled by a conjugacy class of Sn, which means that it's given by a product of cycles. However, if you take n to be very, very large, which is what we want to do, then you are good to study just single cycle. Just like in n equal 4 Superior-Mills or your gauge theory, large n, you just study single trace. Everything else will come from exponentiating that. So we're only interested in single cycle states. What is more, if you have a supersymmetric theory, there is a standard way, like this one is supersymmetric, to look at a state with a single cycle of size, let's say L. In this cycle, we have to put some twist field that gives you the twisted boundary condition that make your field cyclic. But we can dress it in such a way to get essentially a distinguished ground state which is supersymmetric. The twist field carries some energy, it's not BPS. It carries energy but not R charge. We can create some definite ground state which has a size L cycle, and it happens to have dimension L and R charge L. So it's our vacuum of the twist L sector, which I call 0L, which is supersymmetric. And then on top of this vacuum, we can just act with modes of the various fields. And because we are in this twisted sector, the boundary condition that these fields feel, they feel that if you are on the first copy of the theory, you go to the second. And if you're on the second, you go to the third, all the way to the L. So their modes are not quantized in integers, they are quantized in 1 over L, because essentially they fill a base space that is L times bigger. So they are fractionally moded. These are the bosons. As always, the fermions are more complicated, so there are shifts of plus minus 1/2 that you have to take care of. And the shifts of R charges are chosen in some judicious way. There is a whole story about Ramond and the nice sectors that I'm not going to tell you. But that's more or less how you can construct your state. You just act freely with a bunch of oscillators. They are free oscillators. Modulo a condition, which is basically a condition of orbifold invariance. It tells you that the total mode number of the left and the total mode number of the right, or antichiral, their difference should be 0 modulo L. This is a way that you construct the spectrum, and the spectrum that you find is actually pretty simple. So this is my state. The spectrum here is just the sum of Ni over L plus the sum of N tilde over L. You just sum up all the mode numbers, essentially, right? Just as if we were a free theory, you have to just divide by L. If we go back to our dispersion relation, and you put h equals 0 and k equal 1, our dispersion relation, we have only one type of particle, the one with mu equals 0. The dispersion relation is super simple. It's just 1 over 2 pi modulus of p. And you see immediately that you can reproduce this free theory by putting free quantization condition for the momenta p, 2 pi nu over j. You put it here. If mu is positive, is n. If mu is negative, is n tilde. And you reproduce everything for the free theory. That's fine, but the free theory, as far as the spectrum goes, is quite boring. So can you do better? Can you understand how you deform a wave and introduce the interesting interacting dynamic? Well, I told you that from integrability, deforming a wave means that you have to turn on some non-trivial anticommutator between G and G tilde, which is something that might look very odd from a conformal field theory standpoint. But there is a way to realize this. There is a marginal operator which comes from the twist 2 sector, from a 2 cycle, dressed in some appropriate way, that will give you something like this. It will deform in a very complicated way the energies of the states, and it is also the one that is known to correspond to turning on Ramond-Ramond flux. So I'm not going to tell you what it is, but I'm just saying you look up what it is, you deform your, in principle, action by this lambda, and then you do conformal perturbation theory. This lambda is some deformation parameter which will have to be related to h. So there will be some function h of lambda that, in the way that I wrote it, will have to be linear with possible corrections. So what do we want to see in this deformed theory? We want to see that when you act with the G tilde, with the right supercharge on an alpha, on a left mode, you don't get 0. This guy doesn't just anticommute, hit the vacuum and kill it. But we get something non-trivial. We get some other left psi. And then if you work out the charges, for instance, you see that this G tilde has a plus dot, as charge under the SU2R symmetry. In order to balance these charges, the only thing that you can do is that you have to relate this expression here, which is on the vacuum of length L, to the one of length L plus 1. Again, this is exactly what you have in what we discussed before. So this action is supposed to make sense only in the L to infinity limit. It's also very similar to what they have in equal superior Mills. For people that are familiar with it, is the length changing. And this coefficient C and L is really the representation coefficient. So what you want to do is that you should take this C and L, you compute it in some way. You take L to be large because that's necessary. You take N to be large so that you have a P, a momentum which is 2 pi N over L, which is fixed. And this should match the representation coefficient that we used in integrability to fix the S matrix also many years ago. So the type of computation that gives you this object, very sketchily, is this. You first want to do this computation in conformal perturbation theory, so you're going to integrate over this deformation operator inserted wherever. At 0, you put your original state, the boson of length L. At infinity, you put what you should get out, the fermion of length L plus 1. and you act with the supercharge. And this is a fairly complicated computation, but it can be done. This computation was actually done many, many years ago by Gava and Narain, but they did it in a specific regime where n over L is small. And also they were trying to match with the wrong theory. Now we know they were trying to match with the theory at k equal to 0, which is not exactly the orbifold. It was redone very recently by Gaberdielgo, Pacuman, and Naers. They computed for n over L fixed, so that's what you need. There are some manipulations that don't look quite correct when they try to take the limit L to infinity, but one way or another they get a result that seems to be correct. And then they matched essentially with the orbifold, with the correct theory, but they didn't quite identify the correct representation and integrability. So very shortly afterwards, we actually sort of fixed this issue, and we showed that they have reproduced indeed the S matrix that we know from integrability, and they fixed the first coefficient of this expansion to be precisely 1. It's hard to see whether there are more coefficients. Just very, very briefly, I promised something about k equal to 0. So just to tell you, the dispersion at k equal to 0 was this lattice dispersion. And an interesting thing is that if you look what are the leading corrections at small h, the anomalous corrections, they are not when mu is, they are when mu is precisely 0, because you get h rather than h squared. So it seems that they come from the mu equals 0 modes. These are precisely the T4 modes. So you say, haha, symmetric orbifold of T4 again. Not quite. So what we did, very briefly, we took the equation that described the complete spectrum. We expanded those equations. We solved them at linear order in H. And we look at the energy of these modes. It's a system of equations that we can only solve numerically. And that's how they look like. Forget about the blue cross. I don't have time to explain it. But the dotted line is what you will get for a free particle with dispersion sine p over 2. And you see that the dots, they do something complicated. They are not linear as you would have in a symmetry product orbifold. They are not on the free line. They are just some interacting theory. We also did something more. We looked at a spectrum of more and more excitations, because we wanted to check whether if you put more excitation, the energy just adds up, or whether there is some binding energy, some interaction. And there is interaction. So this is some interacting theory that looks like lattice-like, and is the weakly coupled dual of this D1, D5 system, which looks like some integrable model yet to be understood and discovered. Because I'm out of time, I leave you with a slide with a little bit of a summary on the pure NSNS, that is the Wiener model, where everything is clear. The Ramond-Ramond, where we have the spectrum from integrability, but we don't understand the dual, and the mixed flux case, which is, of course, the richest, where there are many things to be understood. And the reference that I skipped are all in this paper, as well as more explanations. So I'll just leave this on, and thank you very much for your time.
Any questions?
What is the operator D2 in slide 19 in terms of the fundamental fields?
The deforming operator. So is the twist 2, which has dimension 1/2, as it happens, dressed by two supercharges with all the indices contracted so that it is neutral under R charge and under whatever other SU2s you have in the game. Then it has dimension 1/1, you can integrate it.
And why does it turn on Ramond-Ramond flux?
So that's not obvious. It's an analysis that you can do. It was, I think, originally done by Larsen and Martinet. They look at the sort of moduli. But if you don't believe it, you just go by exhaustion, and there are essentially 20 operators, 16 of which they don't do anything. They change the shape of the torus. And 4 of which come from this twist 2 sector. They just have different charges, and they all turn on Ramond-Ramond flux in some way. So it's easy to see that essentially only if you have non-trivial twisted sector, you get this effect. Another way is that you see here that I'm linking a state with of size L and one of size L plus 1. I can only do that if I put something that is of size 2. Those are the rule of how you do the OP of twist fields.
Out of curiosity, because if I start with ADS3 background and I apply non-abelian duality in the non-compact direction, I do get ADS2 cross one line. So I was wondering whether you have already, and non-abelian duality, of course, commutes with integrability. So I'm wondering whether you have already thought about applying the same kind of techniques to ADS2.
It's something that is among the things that we are thinking about. It becomes a little bit complicated because you lose, of course, some of the explicit symmetries that we have. But because, as you say, this preserves integrability, really you're not lost them, you have encoded them in some way. So that's something that actually is very interesting and we want to look at. Yeah.
Any other questions? Did you want to
Okay,
ask something?
perhaps a last thing that I tell you, unrelated to the talk. So I'm very happy to announce on behalf of the construction theory challenges and on behalf of, as well of Nordita, the next edition of Eurostrings will take place at Stockholm and Nordita, and it will be August 25 to 28, 2025. It's already on the String Wiki. If you don't remember the date, you can find it there. But yeah, hope to see you all there.
Thank you. Let's thank the speaker again.